So in this video, we're going to talk about geosynchronous and geostationary satellites. So geosynchronous, geostationary satellites. Geostationary satellite, if this is a equator, so geostationary satellite orbits just above the equator. So the plane of this equator is parallel to the orbit of the geostationary satellite. And also the other point is that it takes 24 hours for this satellite to orbit the Earth. That means for a person standing here, as it orbits, and the satellite will be above that person continuously in all 24 hours time. So that's a major benefit of the geostationary satellite because for TV and GPS systems, it's quite useful because if you are a person here using a TV antenna, you don't have to keep on changing your TV antenna all the time because the satellite is always above you. Because when you come here, your satellite will be here. When you come here, the satellite will be here because the geostationary satellite takes 24 hours to orbit the Earth, and it takes 24 hours for Earth to rotate. And then your synchronous satellite is quite similar because it also have the same altitude and it takes 24 hours to orbit the Earth. But unlike the geostationary satellite, in geosynchronous satellite, if we have say one person standing here and the geosynchronous satellite is that just above that person, but as the orbits move here, as the satellite moves here, because Earth is rotating from west to east, so let me put that here. The Earth rotates on this axis this way. So only once a day you will see that satellite is just above a one particular point because as it moves, it will be above another point. So, but in geostationary satellite, the satellite is above a point all the time. So that's the advantage of geostationary satellite. But geosynchronous satellite has its own benefits, particularly to cover areas with higher altitudes like mountains and all. And this angle, the angle between the equator and the angle of a geosynchronous satellite is called angle of inclination. That's angle of inclination. So you will find satellites, geosynchronous satellites at different angles. So there's another point it's very worth to consider is that the geostationary satellite is a type of geosynchronous satellite because geosynchronous satellite takes 24 hours to orbit the Earth, and geostationary satellite is also takes 24 hours to orbit the Earth. The only difference is the angle of inclination is zero for a geostationary satellite. So we can say that geostationary satellite is a subset of geosynchronous satellite. So this is a low Earth orbit satellites, LEO. So we discussed these geosynchronous and geostationary satellites, which are about 36,000 kilometers from the center of the Earth. And the low Earth orbits range from 200 to 1,800 or 2,000 kilometers. And sometime we say after 2,000 is the kind of a um, mid-Earth orbits, but we're looking at low Earth orbits. So low Earth orbits are obviously close to the Earth and they have got some special applications. The very popular ones that we all familiar with is the International Space Station and the Hubble telescope. Hubble telescope. So International Space Station is about 400 kilometer altitude and Hubble telescope is 600 kilometer altitude. So compared to the geosynchronous orbit, where we have got 36,000 kilometer, these are quite low values. It's not far from the Earth's surface. So what do we use that for? International Space Station, obviously it's used for lots of scientific research, and Hubble telescope is used for planetary research and also to find out about the beginning of the universe, and lots of things we are able to do from the Hubble telescope the because it's 600 kilometer, it's just above the Earth's atmosphere. So it's quite clear that we should be able to do a good job from the Hubble telescope instead of having the telescopes on Earth, because we will have a clear pictures of the universe from the Hubble telescopes. And what are the other use of LEOs? LEOs are used for mining, like to monitor the um, minerals on Earth, and it's used for military, and it's used for communications. And one of the main advantage of this low Earth orbit is because it's not far from the Earth's surface, it's easy for us to take very sharp, clear images. So, say imaging. And many other benefits. There are so many hundreds of low Earth orbit satellites, and some of them are in constellations. And low Earth orbits, we found out that this one takes 24 hours to orbit the Earth, but low Earth orbits satellites takes a couple of hours to orbit the Earth. One of the problems with this low Earth orbit is that orbital decay. So what is orbital decay? So if you have a satellite orbiting the Earth, as it orbits the Earth, because of this Earth's atmosphere, there's an atmospheric drag that basically opposes the motion of the satellite, and it brings the satellite down to a low orbit. So that happens to many low Earth orbit satellites. So what we normally do, if this is a satellite, we fire a rocket. So there's a Newton's third law. So if you fire a rocket this way, and the satellite will move this way. So we give a boost. So that boost will take the satellite from this orbit back to this orbit. So that's a standard procedure that we do for low Earth orbit satellites.
So this question is to find out the orbital radius of a geostationary satellite. So this is Earth, and this is where the geostationary satellite is, and this is the orbit, and that's the radius. So what we want to find out is the radius of this geostationary orbit, 6,000. But we are going to find out using the Newton's gravitational equation. So let's assume that the radius is r. So what we know about the geostationary satellite? Geostationary satellite takes about 24 hours to orbit the Earth. So it is parallel to the equator. That means it stays on the same position all the time. So that means that if a person is standing here, and it'll be there, and when the person is here, it'll be there, it'll be here, it'll be here. So because it takes 24 hours, so what we know about the satellite is that T is 24 hours. So let's write that down. So T is 24 hours.
So now what we're going to do is that because this is in circular motion, there's a centripetal force, Fc. And the centripetal force is provided by the gravitational force. So what is gravitational force? Which is equal to, uh, if this is m, this is m, this is the mass of Earth and the mass of the GEO satellite. So Fg is equal to gm m over r squared. So centripetal force is equal to mass time acceleration. So Fc is equal to mass of the satellite, v is the velocity, that's the linear velocity, over r. And we also know that v can also be given by v is equal to 2 pi r t. So these are the three equations we're going to use to find the um, the relationship between the period and the radius. So what we are going to do now here is we're going to equate this Fc and Fg. So mv squared r is equal to gmm over r squared. So if we separate v squared here, it's going to be gm over r. So instead of v squared, we're going to put 2 pi r t. So it's 2 pi r t whole thing squared is equal to gm over r. So from here, we get 4 pi squared r squared t squared is equal to gm over r. These equations, in some cases, people memorize this equation for the velocity, which is gm over r, this one, because you can give velocity as square root of gm. You can memorize it, and then you can use the formula uh, to derive that relationship with the t. Um, but in all cases, it's always good to remember this one. Centripetal force is equal to the gravitational force. So you know the gravitational force is given by gmm over r squared, and this is given by mb squared over r. So we can easily derive these equations from first principles. So from here we get t squared is equal to 4 pi squared r cubed divided by gm. So we know that t is 24 hours. So we have to convert that into seconds. So what we get from here is, say we write that again, t squared is equal to 4 pi squared r, r cubed divided by gm. So r cubed is equal to gm t squared divided by 4 pi squared. So r is actually gm t squared over 4 pi squared. So here we know t, this is the mass of the earth, we know pi. So when we get r, that is the distance from here to here, from here to here. So when we get the orbital radius, that's the radius that we are looking for. In case if they ask for the altitude, we need to take the radius and take away the radius of Earth to find the altitude. But here we were asked what is the orbital radius of a geostationary satellite, so which means the distance from here to here. So the answer is equal to, we get around 4.22 times 10 to the power 7 meter. So that is the orbital radius. So if we are asked to find the altitude, we need to take away. So if we consider the altitude as h, that's going to be r minus the radius of Earth. So we have found that the orbital radius is 4.22 times 10 to the power 7, and the radius of Earth is 6.37 times 10 to the power 7 meter. So we will get 3.59 times 10 to the power 7 meter. So we got the orbital radius, which is 4.22 times 10 to the power 7 meter, which is from the center of Earth to the the satellite on orbit, and this is the altitude. So we need to deduct the radius of Earth from the orbital radius to find the altitude. So in summary, we have discussed about geostationary orbit satellites and low Earth orbit satellites. And in geostationary Earth orbit satellites, we also talk about geosynchronous orbit satellites, which is basically in inclined orbits. Geostationary orbits will be parallel to the Earth equator. So this will be in an angle. And low Earth orbit satellites will be at an altitude ranging between 300 to 1800 kilometer. And geostationary or geosynchronous are 36,000 kilometer, and it takes a day for this orbit to complete. And one orbit takes about a day, exactly one day, which is 24 hours, but low Earth orbits take just a couple of hours. And the applications of GEO is mainly for GPS, television, and other communications, uh, and weather. LEOs, the two popular ones that we are all aware of are the International Space Station and the Hubble telescope. And there are hundreds of other LEOs. So what are they used for? LEOs are used for mobile communication. LEOs are used for monitor mining minerals because it's close to Earth. It's easy to monitor it, so we can say mining. And it's used by military to monitor activities, and it's quite useful to capture images in a very high resolution, so we can say imaging. And also it's useful weather forecast. So that's LEOs, and we got GEOs, and that's a summary of it. Remember that these satellites go through a circular motions around Earth. So we can use the Newton's universal gravitational law, which is the force is equal to G times m over r squared, and so the centripetal force is provided by that gravitational force. By equating that, we can find the orbital velocity, orbital period, using the mass of Earth or any planet the satellite is orbiting around. And also, at any point, we can find the potential energy of the satellite or the kinetic energy of the satellite, because the total energy of the satellite at any place is equal to the potential energy plus the kinetic energy. So the total energy is equal to kinetic energy time plus potential energy.